Hello there, and welcome to Ancient Depths, where quiet curiosity meets the deep end of science and wonder is allowed to take its time. Tonight, we're going to look up at something familiar, something that's been hanging in our sky for as long as humans have had eyes to see it, the moon. Singular. Our moon. The only one we've ever known. But what if it wasn't always alone? What if long before cities and agriculture and written language, before mammals walked upright, before the dinosaurs, even Earth had two moons? Not one pale companion tracing its arc across the night, but two, dancing, orbiting, casting double shadows on an ancient ocean that had never seen a single footprint. This isn't mythology. It's not science fiction. It's a question being asked seriously by planetary scientists, geologists, and astronomers who study the early solar system. A question that emerges from craters and chemistry, from computer simulations and the strange asymmetry of the moon we have left. Because our moon, it turns out, is oddly lopsided. Its near side and far side don't match, and that mismatch, that subtle wrongness, has led some researchers to wonder whether our moon might actually be two moons, fused together in a slow ancient collision we never witnessed. I don't mean a dramatic crash, not an explosion or a catastrophic impact. I mean something gentler, stranger. Two bodies, both orbiting Earth, gradually spiralling toward each other over millions of years, until one day, moving at barely walking speed, they touched, and stuck, and became the moon we know today, its surface telling a story in two chapters written by two different worlds. Before we begin to explore what might have happened up there in the deep past, I'd love to know where in the world you're listening from tonight, and whether you can see the moon right now from where you are. Funny, isn't it? The topic is ancient celestial mechanics, and yet here we are, separated by miles and time zones, quietly sharing this same moment under the same sky. No matter where or when you are, I'm glad you're here. If this kind of slow-burn cosmic question is your kind of question, I'd be thankful if you tapped like or subscribed. It helps this sleepy little signal reach other curious minds. No pressure, of course, just an invitation. Like the faint pull of gravity that might, once upon a time, have drawn two moons together. So settle in, maybe lie back if you can, and let your thoughts drift upward to that bright disk hanging in the darkness. We're going to take a long look backward, not through human history, but through the cold mathematics of orbits and the patient testimony of stone. Because before we can ask whether someone came before us, we have to understand just how much time we're dealing with, and how good this planet is at wiping the slate clean. And when you look up at the moon tonight, you're seeing something unusual. Not just beautiful, not just familiar, but genuinely strange in the context of the solar system. Most moons are small, tiny really, captured asteroids, bits of debris, fragments that happen to fall into orbit around a larger world. But our moon is huge. It's about 1/4 the diameter of Earth. That's enormous compared to almost any other moon relative to its planet. Jupiter has dozens of moons, but even its largest, Ganymede, is only about 1/26th the diameter of Jupiter. Saturn's Titan, impressive as it is even smaller relative to Saturn. Mars has two moons, Phobos and Deimos, and they're basically rocks. Potato-shaped, lumpy things barely worth the name, but Earth, small rocky Earth, has a companion so large that some scientists don't even call it a moon. They call it a binary planet system. Two worlds, one much smaller than the other, locked in an eternal dance. This raises a question. How did we get such a large moon in the first place? For a long time, that question didn't have a satisfying answer. There were theories, of course. Maybe the moon formed alongside Earth, condensing out of the same cloud of gas and dust that made our planet. But if that were true, the moon's composition should match Earth's more closely than it does, and it should be orbiting in the same plane as Earth's equator, which it isn't. Maybe the moon was captured. Maybe it formed somewhere else in the solar system and wandered too close to Earth, falling into orbit. But capturing an object that large is incredibly difficult. The physics don't really work. An object passing by Earth would either swing past and keep going, or it would crash directly into the planet. Getting it to slow down just enough to settle into a stable orbit without colliding requires very specific conditions that don't seem to have existed in the early solar system. Or maybe, just maybe, the moon was born from violence. This is the currently accepted theory. and it's called the giant impact hypothesis. It goes like this. About 4.5 billion years ago, not long after Earth itself had formed, another planet, roughly the size of Mars, was also orbiting the Sun. Scientists have named this lost world Theia, after the Greek Titan who was the mother of the moon goddess Selene. Theia's orbit, for reasons we don't fully understand, brought it closer and closer to Earth until one day the two collided. Not a head-on collision, but a glancing blow. Theia struck Earth at an angle, and the impact was so violent that both worlds were partially vaporized. Huge amounts of material, molten rock, vaporized liquid metal, were thrown into space, forming a massive disk around what was left of Earth. And from that disk, over time, a new body condensed, the Moon. This theory explains a lot. It explains why the Moon is so large. It's made from the combined material of two planetary bodies. It explains why the Moon's composition is similar to Earth's mantle, but missing the heavy metals that sank into Earth's core. Those metals stayed with Earth during the collision. It explains why the Moon is moving away from us slowly, a few centimeters per year. The angular momentum from that ancient impact is still playing out, still unwinding billions of years later. But it doesn't explain everything. And that's where the idea of two moons begins to creep in. Because the moon we have, the one hanging in the sky tonight, is lopsided. Its near side, the side we always see, is relatively smooth, covered in dark plains of ancient lava called Maria. Its far side, the side we never see from Earth, is rough, heavily cratered, mountainous. The crust on the far side is thicker. The terrain is older. It's as if someone took two different moons and stuck them together, back to back. For a long time, scientists assumed this asymmetry had to do with Earth's gravity. Maybe tidal forces shaped the moon unevenly as it formed. Maybe the near side cooled differently because it was always facing Earth, but those explanations never quite fit. The differences are too stark. The crust is too thick on the far side. The surface features don't line up with what we'd expect from tidal heating alone. And then, in 2011, a team of researchers proposed something radical. What if the moon's asymmetry exists because the moon isn't one object? What if it's two? Not now, obviously. Now it's clearly a single body, but what if, in the distant past, Earth had two moons, and those two moons slowly, gently collided and merged into the single moon we see today? This idea, sometimes called the twin moon hypothesis, or the Big Splat, suggests that when Theia hit Earth and created the debris disk, not one moon formed, but two a large one, and a smaller companion, perhaps a third of the size. Both would have orbited Earth, both would have been made from the same material, but they would have been distinct, separate bodies. And for a while, millions of years maybe, they coexisted. Two moons in the sky, one bright and large, the other smaller, dimmer, trailing behind or leading ahead. You could imagine standing on that ancient Earth. No life yet, no oxygen in the atmosphere, just rock and heat and water, beginning to collect in basins, and looking up to see two pale crescents hanging in the darkness. But orbits aren't forever, they shift, they decay, they interact. And if two moons were orbiting Earth at slightly different distances, moving at slightly different speeds, their gravitational interactions would have tugged at each other, slowly, patiently over millions of years. Eventually their orbits would have converged, they would have drawn closer, and one day, inevitably, they would have touched. Not a high-speed impact, not a collision like the one that created them. By the time they met, their relative velocity would have been incredibly slow walking speed maybe, jogging speed. The smaller moon would have drifted into the larger one, its surface pressing against the surface of its sibling, and instead of shattering, instead of exploding, they would have simply stuck together. The smaller moon's crust would have piled up onto the larger moon's surface, thickening the crust, creating mountains, altering the shape of the world. This is what they call the Big Splat. Not a bang, but a slow, soft collision. A merger. And if it happened, if Earth really did have two moons that became one, then the evidence should still be there, frozen into the moon's geology, written into the thickness of its crust, visible if you know where to look. We'll explore that evidence shortly. But first, we need to understand something fundamental about how moons form in the first place, and why having two of them, even briefly, isn't as strange as it might sound, because the early solar system wasn't the orderly place we see today. It was chaos, and in chaos, strange things happen. The solar system we know now, the one with 8 planets orbiting peacefully in their lanes, moons tucked into stable orbits, asteroids mostly confined to a belt between Mars and Jupiter. This is the calm after the storm, but 4.5 billion years ago, when the sun was still young, the solar system was a violent, crowded place. Planetesimals, small rocky bodies, were everywhere, constantly colliding, merging, breaking apart. Planets were still forming. Orbits were still stabilizing. And impacts, massive, world-shattering impacts, were common. This period is sometimes called the Late Heavy Bombardment, though that term is more specific to a slightly later phase. The broader era is just the age of accretion, the time when planets were being built from the collisions of smaller objects. Every planet, every moon, every solid body in the solar system bears the scars of this time. Mercury is covered in craters. Mars has a massive impact basin in its northern hemisphere. Earth's surface has been reshaped so many times by tectonics and erosion that most of the evidence is gone, but it was hit too, over and over. And the moon, which has no atmosphere, no plate tectonics, no erosion to speak of, still carries the record of those ancient impacts. Its surface is a museum of violence. Every crater, large or small, is a timestamp, a record of something that fell from the sky and struck stone. In this kind of environment, it's not hard to imagine multiple moons forming around a planet. When Theia hit Earth and ejected material into orbit, that material would have formed a disk, similar to the rings around Saturn. And from that disk, objects would have begun to clump together. Small pieces would have stuck to other small pieces, growing larger, their gravity pulling in more material. Most of that material would have eventually coalesced into a single large moon, but not necessarily all of it. Computer simulations of the impact, the ones that try to recreate what happened when Theia struck Earth, often produce not one moon, but several small moonlets, orbiting alongside one larger body. Most of those smaller objects wouldn't last. They'd crash back into Earth or collide with the main moon. But one, if it formed in just the right place at just the right distance, might have survived. For a while. This isn't just speculation. We see similar processes happening elsewhere. Saturn, for example, has dozens of small moons orbiting within and near its rings. Some of them are called shepherd moons because their gravity helps shape the rings, keeping them confined. These moons are tiny, just a few kilometers across, and they're constantly interacting with each other and with the ring material. Some will eventually collide. Some will merge. The system is still evolving even now, billions of years after it formed. Jupiter's moon system is also dynamic. Some of its smaller moons are thought to be captured asteroids. Others might be fragments of larger moons that were shattered by impacts. The point is, having multiple moons, or having moons that collide and merge, isn't unusual. It's part of how moon systems evolve. So the idea that Earth might once have had 2 moons isn't radical. It's just applying what we know about orbital dynamics and accretion to our own planet's history. The radical part, the part that requires evidence, is the claim that those 2 moons merged in a specific way that left a specific signature in the moon's geology. And that's where things get interesting. Because if the 2-moon hypothesis is correct, then the moon's asymmetry, the difference between its near side and far side, isn't a mystery. It's a memory of the day 2 worlds became one. We'll look at that asymmetry more closely in just a moment. But before we do, it's worth pausing to think about what this means, not just scientifically, but imaginatively. If Earth really did have 2 moons, even for a few million years, then the sky was different once, the tides were different, the night was different, and anyone standing on that ancient lifeless Earth, if anyone could have stood there, would have looked up and seen something we've never seen. Something no human will ever see. 2 moons drifting slowly together, their shadows crossing, their light mingling until the day they touched and became one. It's a strange thought, but then the universe is full of strange thoughts, and the moon, our familiar constant companion, might be stranger than we ever imagined. When astronauts first orbited the moon in 1968, they saw something no human had ever seen before: the far side, the hidden hemisphere, the side that never faces Earth because the moon is tidally locked, rotating once per orbit so that the same face is always turned toward us. And what they saw surprised them. It looked nothing like the near side. The near side, the one we see every night, has large, dark, smooth plains. Those plains are made of basalt, ancient lava that flowed across the surface billions of years ago and then solidified. We call them Maria, Latin for seas, because early astronomers thought they looked like bodies of water. They're not, of course. They're frozen lava. But they give the near side its characteristic appearance, that mottled pattern of light and dark that some cultures see as a face, a rabbit or a woman. The far side has almost no Maria. It's rough, bright, heavily cratered. Mountains rise in jagged ranges. Impact basins overlap each other, layer upon layer of ancient violence. The crust on the far side is thicker, sometimes by as much as 50 kilometers. It's older, less affected by the volcanic activity, more scarred by impacts that were never smoothed over by lava flows. This difference is dramatic, and for a long time it was puzzling. Why would one side of the moon be so different from the other? If the moon formed from a spinning disk of debris, you'd expect it to be relatively symmetrical. If it cooled uniformly, you'd expect both sides to have similar amounts of volcanic activity. But that's not what happened. One explanation has to do with Earth's gravity. The moon formed close to Earth, and Earth's tidal forces would have affected how it cooled and solidified. Maybe the near side, always facing Earth, stayed warmer longer because of tidal heating. Maybe that allowed more volcanic activity on the near side. Maybe the far side cooled faster, forming a thicker crust that prevented lava from reaching the surface. This explanation works to some extent. Tidal heating is real. We see it on Jupiter's moon Io, which is constantly squeezed and stretched by Jupiter's gravity, generating so much internal heat that it's the most volcanically active body in the solar system. But the moon's asymmetry seems too extreme to be explained by tidal heating alone. The crust is much thicker on the far side than tidal models predict, and the distribution of certain elements, particularly radioactive ones that generate heat, doesn't match what we'd expect if tidal forces were the only factor. So scientists looked for other explanations, and one possibility, proposed in 2011 by researchers Martin Jutzi and Erik Asfaug, is that the moon's asymmetry is the result of a collision. Not the collision that created the moon in the first place, but a second collision, a slow, gentle impact between the main moon and a smaller companion moon. Their idea goes like this. After the Theia impact created a disk of debris around Earth, most of that material coalesced into a single large moon, but some of it, perhaps 2 or 3% of the total mass, formed a second, smaller moon. This second moon, maybe 1,000 kilometers across, orbited Earth at a slightly different distance than the main moon. For a while, both orbits were stable, but the moon's gravity tugs on Earth, causing tidal bulges in Earth's oceans and even in the solid rock of the planet itself, and Earth's gravity tugs back on the moon, causing the moon's orbit to change over time. This is why the moon is slowly moving away from us. Every year it drifts about 3.8 centimeters farther from Earth. The tidal forces between Earth and the moon transfer angular momentum from Earth's rotation to the moon's orbit, causing Earth to spin more slowly and the moon to move outward. This process has been happening for billions of years, and it's still happening now, but in the early solar system things were more complicated. If there were two moons, their orbits would have interacted not just with Earth, but with each other. And there are certain configurations of orbits called Lagrange points, where gravitational forces balance out in interesting ways. One of these points, called the L4 or L5 point, is a stable location where a smaller object can orbit at the same distance from Earth as a larger object, but 60 degrees ahead or behind. If the smaller moon formed near one of these Lagrange points, it could have remained stable for a long time, perhaps tens of millions of years. But Lagrange points aren't perfectly stable. They're more like shallow wells, a small nudge, a gravitational interaction with another object, or just the slow evolution of the system. And the object can drift out of the well and into a different orbit. And that's what Jutzi and Asfaug think happened. Over time, the smaller moon's orbit became unstable. It drifted closer to the main moon. And eventually, inevitably, the two collided. But because they had been orbiting in roughly the same direction, at roughly the same speed, their relative velocity when they collided was very low, maybe 2 or 3 kilometers per second. That sounds fast, but in cosmic terms it's a crawl. A typical asteroid impact happens at 20 or 30 kilometers per second. This was gentler, much gentler. When the smaller moon hit the larger one, it didn't shatter. It didn't explode, it splattered. Its surface crumpled and spread across the larger moon's surface like dough being pressed flat. And because the collision was so slow, so gentle, the material didn't melt. It didn't vaporize. It just piled up, thickening the crust, creating the rough mountainous terrain we see on the far side today. This is the Big Splat hypothesis. A slow-motion collision that added a layer of material to one side of the moon, making it lopsided. And if it happened, it would explain several things at once. It would explain why the far side has a thicker crust. It would explain why the far side has fewer Maria, because the thicker crust prevented lava from reaching the surface. It would explain the rough, mountainous terrain. And it would explain why the moon's centre of mass is offset from its geometric centre, a feature that has puzzled scientists for years. But like any good hypothesis, this one makes predictions. If the two-moon collision really happened, then we should be able to find evidence of it, not just in the thickness of the crust, but in the composition of the rocks, in the distribution of minerals, in the chemistry of the surface. We should be able to test it. And we have, sort of. The evidence is mixed. Some of it supports the hypothesis, some of it doesn't. And some of it just raises new questions. We'll look at that evidence shortly. But first, it's worth thinking about what it would have been like to watch. If anyone, or anything, had been standing on Earth 4.5 billion years ago, and if they had looked up on the night the two moons collided, what would they have seen? Probably not much at first. The collision would have happened slowly, over hours or maybe even days. The smaller moon would have drifted closer, its shape distorting as tidal forces pulled at it. Maybe it would have started to break apart, pieces falling away, spiralling down toward the surface of the larger moon. Or maybe it would have stayed intact, its surface cracking, crumbling as it pressed against the other world. There wouldn't have been a flash of light, no explosion, no shockwave rippling across space. Just two spheres of rock, meeting in the darkness, their surfaces grinding together, merging, becoming one. And when it was over, when the dust and debris had settled, there would have been one moon, larger than before, lopsided but whole, and from Earth, looking up, you might not have noticed any difference at all. Just a bright disk in the sky, unchanged, eternal, as it had always been. But if the moon would have known, the moon would have remembered, and billions of years later, when humans finally reached its surface and began to study its rocks, that memory might still be there, written into the stone. Let's talk about what it takes to get two moons to collide. Because this isn't something that happens easily or quickly. Orbits are stable, mostly. Once an object is in orbit, it tends to stay there, tracing the same path over and over, sometimes for billions of years. The moon, for example, has been orbiting Earth for roughly 4.5 billion years. And in all that time, its orbit has changed, yes, but gradually, predictably. It hasn't suddenly crashed into us or flown off into space. But stability isn't the same as permanence. Orbits can change. They do change. And when you have two objects orbiting the same planet, especially if one of them is much smaller than the other, the system becomes more complicated, more fragile. The key concept here is orbital resonance. This is when two orbiting bodies exert regular periodic gravitational influences on each other. Imagine you're pushing someone on a swing. If you push at just the right time, in rhythm with the swing's natural motion, even small pushes can build up over time, making the swing go higher and higher. That's resonance. The same thing happens with orbits. If two moons are in resonance, meaning their orbital periods are related by a simple ratio like 2:1 or 3:2, their gravitational interactions can amplify over time, changing their orbits in ways that wouldn't happen otherwise. Resonances can stabilize a system. Jupiter's moons Io, Europa and Ganymede are locked in a 4:2:1 resonance, and this actually helps keep their orbits stable despite the intense gravitational environment around Jupiter. But resonances can also destabilize a system. They can pump energy into an orbit, making it more elliptical, more chaotic, more likely to cross paths with another object. In the case of Earth's two hypothetical moons, the smaller one might have started out in a stable orbit, perhaps near a Lagrange point. But over time, interactions with Earth, with the larger moon, or even with the Sun, could have pushed it out of that stable configuration. His orbit would have started to drift. And once it drifted far enough, it would have entered a region where the gravitational pull of the larger moon became dominant. At that point, the outcome was inevitable. The smaller moon's orbit would have decayed, slowly spiralling inward, until eventually it met the larger moon. The exact timing would have depended on a lot of factors: the initial distance between the two moons, their masses, the shape of their orbits, even the rotation rate of Earth. But the end result would have been the same: collision, merger. Computer simulations of this process, the ones run by Jutsi, Asfaug and others, suggest that the whole thing would have taken millions of years. Not the collision itself, which would have happened relatively quickly once the two moons got close enough, but the orbital decay, the slow drift from stability to collision, that would have been a long, patient process. During that time, if you could have watched from Earth, you would have seen the smaller moon gradually getting closer to the larger one. Month by month, year by year, century by century, the gap would have narrowed. Eventually, the two would have appeared to touch, their edges overlapping in the sky. And then, one night, they would have merged. The smaller moon would have disappeared, absorbed into the larger one, and the sky would have looked different, emptier. But here's the thing: even if this happened, even if Earth really did have two moons and they really did collide, it wouldn't have been recent. It would have happened very early, probably within the first 100 million years after the moon formed. Because orbital dynamics work on specific timescales and the kinds of orbits that would have allowed two moons to coexist, we wouldn't have lasted much longer than that. This is important because it means we can't just look at the moon today and see the collision. The surface we see now, the craters, the mountains, the Maria, all of that formed later. The collision would have happened first, reshaping the moon's basic structure, and then billions of years of impacts and volcanic activity would have covered it, buried it, modified it. So the evidence we are looking for isn't obvious. It's subtle. It's hidden in the details, in the thickness of the crust, in the composition of certain minerals, in the gravitational field of the moon. Measured by orbiting spacecraft, we are looking for patterns that shouldn't be there if the moon formed as a single body, but make sense if it's actually two bodies fused together. And we're looking at data from missions that weren't designed to test this hypothesis. The Apollo astronauts weren't trying to prove or disprove the two-moon idea. They were just collecting samples, taking measurements, trying to understand the moon in general. But science works like that sometimes. You collect data for one purpose, and later, someone asks a different question and realizes the data can answer it. So what does the data say? Does it support the two-moon hypothesis? Does it rule it out? Or, like so many things in science, does it leave us somewhere in the middle with more questions than answers? The answer, unsurprisingly, is complicated. Some of the evidence fits, some of it doesn't, and some of it is still being debated. Let's start with what fits. First, the thickness of the crust. We know from gravity measurements taken by spacecraft orbiting the moon that the crust on the far side is significantly thicker than the crust on the near side. In some places, it's 50 kilometers thicker. That's a huge difference. And it's hard to explain if the moon formed as a single symmetrical body. The two-moon hypothesis offers a straightforward explanation. The smaller moon collided with the larger one. Piling its material onto the far side, that material became part of the crust, thickening it. The impact was slow enough that the material didn't melt or mix with the underlying rock, it just stacked on top, like adding another layer to a cake. Computer simulations of this process show that it could work. Jutsi and Asfaug ran detailed models of a low-speed collision between a large moon and a smaller companion, and they found that the result looked a lot like the moon we have today. The far side ended up with a thicker crust. The near side remained relatively smooth. The overall shape of the moon became slightly lopsided, which matches observations. Second, the distribution of Maria. The near side has large, dark plains of basalt. The far side has almost none. This makes sense if the crust on the far side is thicker, because a thicker crust would make it harder for lava to reach the surface. When the moon was young, its interior was still hot. Molten rock could rise through cracks in the crust and flow out onto the surface, creating the Maria. But on the far side, where the crust was thicker, the lava couldn't make it through. It got trapped below the surface, or it cooled and solidified before it could erupt. Third, the composition of the crust. Samples collected by Apollo astronauts and analysed in labs on Earth show that the highlands, the bright mountainous regions that cover much of the moon's surface, are made of a type of rock called anorthosite. This rock forms when certain minerals crystallize out of molten magma and float to the surface. The fact that the highlands are rich in anorthosite suggests they formed early, when the moon was covered in a global ocean of magma. But here's the interesting part. The highlands on the far side have a slightly different composition than the highlands on the near side. They're enriched in certain elements, particularly aluminum and calcium. This could be explained if the far side highlands came from a different source, a smaller moon that merged with the main moon and brought its own distinct chemistry with it. Fourth, the shape of the moon. The moon isn't a perfect sphere, it's slightly elongated with one axis longer than the others. This is partly due to tidal forces from Earth, which stretch the moon slightly in the direction of Earth. But the moon is also offset. Its centre of mass doesn't line up with its geometric centre. It's shifted about 2 kilometres toward Earth. This asymmetry is consistent with the moon being lopsided, with extra material piled up on one side. So far so good. The evidence seems to support the two-moon hypothesis, but there are problems, things that don't quite fit, things that make scientists hesitate before fully accepting the idea. One problem is the age of the crust. If the far side thickened because of a collision with a smaller moon, then the rocks in the thickened region should be younger than the rest of the crust. They should show signs of being added later. But dating rocks from the moon is difficult, and the available data doesn't clearly show this pattern. Some far-side rocks seem to be the same age as near-side rocks. This doesn't necessarily rule out the two-moon hypothesis, but it complicates it. Another problem is the lack of a clear impact site. When two objects collide, even at low speed, you'd expect to see some kind of scar, a depression, or a raised rim, something that marks where the impact happened. But the far side of the moon doesn't have an obvious feature like that. It's rough and mountainous, yes, but there's no single large structure that looks like the result of a moon-sized collision. Supporters of the two-moon hypothesis argue that the collision was so gentle and happened so early that any obvious impact features were erased by later geological activity, volcanic eruptions, smaller impacts, tectonic adjustments. All of these could have smoothed over the original collision site, but this argument relies on a lot of assumptions and it's hard to test. A third problem is the chemistry. If the smaller moon had a different composition than the main moon, we should see clear chemical signatures of that difference in the rocks on the far side, and we do see some differences, but they're subtle, not as dramatic as you might expect if an entire moon's worth of material was added. This could mean the smaller moon had a very similar composition to the main moon, which makes sense if they both formed from the same debris disk, but it also makes the hypothesis harder to prove because there's less to distinguish the two populations of rock. And then there's the timing. The two-moon hypothesis requires that the smaller moon existed for long enough to drift into a collision course, but not so long that other processes would have destroyed it. That's a narrow window, maybe a few tens of millions of years. It's possible, but it requires things to happen in a very specific sequence. If the timing was off, even by a little, the scenario falls apart. So where does that leave us? The two-moon hypothesis is plausible. It explains some features of the moon that are otherwise hard to account for. But it's not proven. There are other explanations for the moon's asymmetry, explanations that don't require a second moon. And until we have more data, better samples, more detailed measurements, we can't say for certain which explanation is correct. What we can say is that the moon is more complex than we thought. Its history is longer and stranger, and the idea that Earth might once have had two moons, however briefly, is no longer just a curiosity. It's a serious scientific question, one that researchers are actively working to answer. We'll return to this question shortly, but first, let's think about what it would have meant to live on a planet with two moons. Not scientifically, but experientially. Because even if it only lasted a few million years, even if no one was there to see it, the presence of a second moon would have changed everything: the tides, the night sky, the rhythms of the world. Let's imagine what that might have been like. Tides are something we take for granted. Twice a day in most places. The ocean rises and falls, high tide, low tide, it's predictable. Reliable. Caused by the moon's gravity pulling on Earth's oceans, creating bulges of water on the side of Earth facing the moon, and on the opposite side the sun also contributes to tides, but the moon's effect is stronger because it's so much closer. Now imagine there are two moons, both pulling on Earth's oceans, both creating tidal bulges. The tides would no longer be simple, They'd be complex, chaotic even, depending on where the two moons were in their orbits. Sometimes the two moons would be on the same side of Earth, their gravitational pulls adding together. The tides would be extremely high, water would surge up coastlines, flooding low-lying areas, retreating only hours later to expose vast stretches of seabed. Other times the two moons would be on opposite sides of Earth, pulling in opposite directions. The tides would be weaker, less dramatic. The difference between high and low tide would shrink coastal areas that flooded during aligned tides would remain dry during opposed tides, and most of the time the two moons would be somewhere in between, neither perfectly aligned nor perfectly opposed. The tides would be intermediate, unpredictable, constantly shifting. If there had been life on Earth during this time, if there had been anything living in the oceans or near the coasts, it would have had to adapt to this variability. No single rhythm would have worked. Survival would have required flexibility, the ability to cope with tides that changed not just daily, but from month to month as the two moons drifted in and out of alignment. Of course, 4.5 billion years ago, there was no life on Earth. The planet was still too hot, too violent. The oceans, if they even existed yet, were likely acidic. Filled with dissolved minerals from volcanic eruptions, there were no organisms to notice the tides, no evolutionary pressure to adapt to them. But the tides would have been there, shaping the planet, moving water, stirring sediments, creating currents that circulated heat and chemicals around the globe. And there's another effect, one we rarely think about. Tides don't just affect water, they affect the solid rock of the planet too. Earth's crust flexes very slightly as the moon's gravity pulls on it. This tidal flexing generates heat deep in Earth's interior. Not a lot of heat, but enough to contribute to the planet's overall thermal budget. If there were two moons, the tidal heating would have been stronger, more variable. Earth's interior might have stayed molten longer. Volcanic activity might have been more intense. This could have had long-term consequences for Earth's geology, for the formation of the continents, for the development of plate tectonics. We don't know. It's speculation. But it's interesting speculation, the kind that makes you realize how interconnected everything is. The presence or absence of a second moon wouldn't just change the night sky, it would change the entire planet. Now think about the sky itself. What would it have looked like to see two moons? We can only guess, but we can make educated guesses based on what we know about orbits and brightness. The main moon would have looked much like it does now, large, bright, dominant. But the smaller moon, if it was about a third the size, would have appeared smaller in the sky, perhaps a quarter or a third the diameter of the main moon, still visible, still significant, but clearly the lesser of the two. The brightness would have depended on the smaller moon's surface. If it was made of the same material as the main moon, it would have reflected light in the same way. But because it was smaller, it would have appeared dimmer, maybe half as bright, maybe less. Not bright enough to read by the way you can sometimes read by the light of a full moon, but bright enough to cast shadows. And the shadows would have been strange. With two moons in the sky, objects on Earth's surface would have cast two shadows, sometimes overlapping, sometimes diverging. Depending on the phase of each moon and their positions in the sky, you might see one sharp shadow and one faint one, or two equally strong shadows crossing each other at odd angles. The phases of the two moons would have been complex as well. Both would have gone through cycles of waxing and waning, but not necessarily in sync. Sometimes both would be full, sometimes both would be new, sometimes one would be full while the other was a crescent. The night sky would have been different every night, not just in the sense that the moon's phase changes, but in a deeper, more unpredictable way. And then there's the question of eclipses. With two moons, eclipses would have been more common, but also more varied. Sometimes one moon would pass in front of the other, creating a moon-moon eclipse, visible from Earth as one disk sliding across another. Sometimes one moon would pass through Earth's shadow, darkening, just like lunar eclipses today. And sometimes both moons would align with the sun, creating a double solar eclipse with two dark disks moving across the sun's face at different speeds. None of this would have mattered, of course, not then. There was no one to watch, no one to build calendars around the lunar cycles, no one to tell stories about the two lights in the sky, but it would have been there. A different sky, a different world. And then one day it would have ended. The smaller moon would have drifted too close, the orbits would have intersected, and the collision would have reduced the sky back to what we know: one moon, one rhythm, one Li, one light. Maybe it's better this way. Maybe having two moons would have been too complicated, too chaotic, too much for life to work with when it finally did emerge. Or maybe we're just used to what we have, and we can't imagine anything different. But the fact remains, if the two-moon hypothesis is correct, then the sky was different once. And that's a humbling thought. It reminds us that even the things we think of as permanent, as eternal, might just be the current state of something that's always changing, always evolving. Next, we'll look at other moons in the solar system, other places where collisions and mergers have shaped the worlds we see today. Because Earth isn't the only planet with a complex moon history, and by looking at what's happened elsewhere, we can better understand what might have happened here. Saturn's moon Iapetus is strange. Even by the standards of moons, which are often strange, Iapetus stands out. It has two faces, one bright, one dark. The bright side is covered in ice, reflecting sunlight like a mirror. The dark side is covered in something else, a reddish-brown material that absorbs light, making it look almost black. The transition between the two is sharp, dramatic. Half the moon looks like it's been dipped in tar. No one is entirely sure why. Theories range from impacts that deposited dark material on one side, to ice evaporating from the warm side and condensing on the cold side, to material falling onto the moon from Saturn's rings. But what's clear is that Iapetus has a history, a complex one, and that history is written into its surface in ways we're still trying to read. Iapetus also has something else strange. A ridge. A massive equatorial ridge that runs around a large portion of the moon. Like a seam. It's tall, up to 20 kilometers high in places, and narrow. Just a few kilometers wide, it looks artificial, like someone built a wall around the moon's equator. But it's not artificial. It's natural. Probably. One theory is that the ridge formed early, when Iapetus was spinning faster. The rapid rotation would have caused the moon to bulge at the equator, and when the rotation slowed down due to tidal forces from Saturn, the bulge froze in place, leaving the ridge. Another theory is that the ridge is the result of material falling onto Iapetus from a ring that once orbited the moon, material that piled up along the equator over millions of years. Or maybe, just maybe, the ridge is the scar of a collision. Not a high-speed impact, but a slow merger, similar to what might have happened with Earth's two moons. Maybe Iapetus is also two moons fused together, and the ridge marks where they joined. This is speculation, of course. There's no strong evidence that Iapetus was once two objects, but the fact that scientists even consider it shows how common this kind of process might be. Moons collide. Moons merge, it happens, and when it does, it leaves traces, even if those traces are difficult to interpret. Then there's Mars. Mars has two moons, Phobos and Deimos, and both of them are small, tiny really. Phobos is about 22 kilometers across at its widest. Deimos is even smaller, about 12 kilometers. They're not spherical, they're lumpy, potato-shaped, covered in craters. They look more like asteroids than moons, and for a long time scientists thought that's exactly what they were. Captured asteroids, objects that formed in the asteroid belt and then wandered close enough to Mars to be pulled into orbit. But there are problems with that theory. Capturing an asteroid is hard, as we discussed earlier, and the orbits of Phobos and Deimos are almost exactly in the plane of Mars's equator. That's not what you'd expect for the captured objects, which usually have elliptical tilted orbits. So maybe they didn't come from the asteroid belt. Maybe they formed near Mars, from a debris disk created by an impact, similar to how Earth's moon formed. And here's where it gets interesting. If Phobos and Deimos formed from an impact, there might have been more of them originally. Maybe Mars had 5 or 6 small moons, or even more, and over time they collided with each other or crashed back into Mars, leaving only the two we see today. Phobos, in fact, is still falling. Its orbit is decaying very slowly, and in about 50 million years, it will either crash into Mars or break apart and form a ring. Deimos, on the other hand, is moving away, gradually drifting into a higher orbit. This dynamic system, with moons colliding and merging and being lost, might be the norm, not the exception. And if Mars, a smaller planet with weaker gravity, can have a complex moon history, then surely Earth, with its much larger moon, could have as well. Jupiter's moon system is another example. Jupiter has 95 known moons, though most of them are tiny, irregular objects that are probably captured asteroids or comets. But the 4 largest moons, the Galilean moons, Io, Europa, Ganymede, and Callisto, are substantial worlds in their own right, and they're in resonance. As we mentioned earlier, Io orbits Jupiter once for every 2 orbits of Europa, and Europa orbits once for every 2 orbits of Ganymede. This 4 to 2 to 1 resonance keeps their orbits stable despite the intense gravitational environment. But that resonance didn't form by accident. It evolved over time as the moon's orbits changed due to tidal interactions with Jupiter. And during that evolution, it's likely that there were other moons, smaller ones, that got caught in unstable orbits and either crashed into one of the Galilean moons or were ejected from the system entirely. In fact, scientists think that the Galilean moons might have formed much closer to Jupiter than they are now, and then migrated outward over millions of years. During that migration, they would have swept through regions where other small moons were orbiting, colliding with them, absorbing them, growing larger in the process. This is called accretion by collision, and it's thought to be a common process in the formation of moon systems. Most of the mass ends up in a few large moons, while smaller objects either merge with the large ones or are lost. The system we see today is the end result of millions or billions of years of this kind of evolution. Earth's moon system might have undergone a similar evolution. The main moon, and possibly a smaller companion, would have formed from the debris disk created by the Theia impact over time. The smaller moon's orbit would have become unstable and it would have collided with the main moon. The result is the single large moon we have today. This process isn't unique to Earth. It's not even unusual. It's just how moon systems work. And that's one of the reasons the two-moon hypothesis is taken seriously. It's not proposing something bizarre or unprecedented. It's proposing something that fits with what we know about how planets and moons evolve. But there's another layer to this. Another reason scientists are interested in the idea of two moons. It's not just about understanding the moon's geology or the history of the Earth. Moon system. It's about understanding the early solar system, the conditions that led to the planets we have today, and the processes that shape planetary systems in general. Because if Earth had two moons, and if those moons collided, then that collision would have happened during a very specific time in the solar system's history. A time when things were still settling down, when orbits were still shifting, when impacts were common. By studying the moon, and by trying to figure out whether it's one object or two objects merged together, we're also studying that early era. We're looking back into the solar system's youth, trying to understand what happened, how it happened, and why the solar system looks the way it does now. And that's part of the larger project of planetary science. It's not just about cataloguing objects and measuring their properties. It's about understanding processes, about figuring out the rules that govern how planets and moons form, evolve, and interact. Because once we understand those rules, we can apply them to other planetary systems, to the thousands of exoplanets we've discovered orbiting other stars, and we can start to answer even bigger questions. Are planetary systems like ours common? Are we typical or unusual? Is the Earth-Moon system, with its large moon and its complex history, rare? Or is it just one example of a pattern that repeats throughout the universe? We don't know yet, but we're getting closer, and every new piece of data, every new simulation, every new sample returned from the moon brings us a little closer to answering those questions. Next, we'll turn to the future, because if the two-moon hypothesis is going to be proven or disproven, it's going to require new missions, new technologies, new ways of looking at the moon. And some of those missions are already being planned. If you want to solve a mystery about the moon, the best way to do it is to go there, to walk on its surface, to pick up rocks, to drill into the ground, to place instruments that can measure everything from seismic activity to the strength of the gravitational field. This is what the Apollo astronauts did in the late 1960s and early 1970s. They brought back 382 kilograms of lunar rock and soil, samples that have been studied in labs around the world for more than 50 years. Those samples revolutionized our understanding of the moon. They told us that the moon is ancient, about the same age as Earth. They told us that the moon's surface was once covered in a global ocean of molten rock, a magma ocean that cooled and solidified to form the crust. They told us about the composition of the lunar interior, about the presence of water in tiny amounts, about the history of impacts and volcanic activity. But they also left questions unanswered, because the Apollo missions only visited a small fraction of the moon's surface, all of it on the near-side 6 landing sites, spread across the equatorial and mid-latitude regions. We have no samples from the far side, no samples from the poles, no samples from the deep interior. And without those samples, there are limits to what we can say about the moon's history. If the two-moon hypothesis is correct, then we need samples from the far side. Specifically, we need samples from the thickened crust, the region that would have been covered by material from the smaller moon. We need to measure the composition of those rocks, to date them, to compare them with rocks from the near side. Only then can we say with confidence whether the far side is chemically distinct, whether it formed at a different time, whether it came from a different source, and that's difficult to date. Because the far side is hard to reach. When you're on the far side of the moon, you're out of direct communication with Earth, so radio signals can't pass through the moon, so you need a relay satellite, something orbiting the moon that can receive signals from a lander and transmit them back to Earth. That adds complexity and cost. But it's not impossible. In fact, it's already been done. In 2019, China's Chang'e 4 mission landed on the far side of the moon, in a crater called von Karman. It was the first spacecraft to ever land there, and it operated for several years, analysing the soil and rocks, taking pictures, measuring the subsurface with ground-penetrating radar. Chang'e 4 didn't return samples to Earth, but China's Chang'e 5 mission, which landed on the near side in 2020, did. It brought back about 2 kilograms of lunar soil, the first new samples in more than 40 years, and China is planning more missions. Chang'e 6, which successfully returned samples from the far side in 2024, is a major step forward. These samples will be crucial for testing the two-moon hypothesis. NASA is also planning to return to the moon. The Artemis program aims to land astronauts on the lunar surface in the coming years, and one of the goals is to explore regions that Apollo never reached, the South Pole, for example, where there might be water ice in permanently shadowed craters, and eventually the far side where astronauts could collect samples from the thickened crust and bring them back to Earth for analysis. But even before astronauts return, robotic missions are providing new data. The Lunar Reconnaissance Orbiter, which has been circling the moon since 2009, has mapped the entire surface in high resolution. It's measured the moon's gravitational field with unprecedented precision, revealing details about the thickness of the crust and the distribution of mass beneath the surface. It's found evidence of recent volcanic activity, of water ice at the poles, of strange magnetic anomalies that hint at a complex geological history. And there are other missions in the works. India's Chandrayaan program, Japan's Slim Lander, private companies planning commercial lunar missions. Each one adds to our knowledge, filling in gaps, answering some questions and raising new ones. The two-moon hypothesis, if it is going to be definitively tested, will require a combination of approaches. We'll need more samples from more locations, especially from the far side. We'll need more detailed gravitational measurements to map the structure of the moon's interior. We'll need better computer simulations, using more powerful computers and more sophisticated physics, to model the collision and see if it really could have produced the moon we see today. And we'll need patience, because science doesn't work on a schedule. Missions take years to plan, years to build, years to execute. Samples take months or years to analyze. Models take time to refine and validate. The process is slow, but it's thorough. And eventually, if we're persistent, if we keep asking questions and collecting data, we'll get an answer. Maybe the answer will be yes, Earth did have two moons, and they did collide, and the evidence is there in the rocks and the gravity and the shape of the moon. Maybe the answer will be no, the moon formed as a single body, and its asymmetry has a different explanation, one we haven't thought of yet. Or maybe the answer will be something in between, something more nuanced, a scenario that combines elements of the two-moon hypothesis with other processes. Whatever the answer, it will tell us something profound, not just about the moon, but about how planets and moons form, about the early solar system, about the processes that shape the Earth we live on. Because the moon and the Earth are linked. They form together, they evolve together. And understanding one helps us understand the other. And there's something else, something harder to quantify but no less important. Every time we learn something new about the moon, every time we send a spacecraft or bring back a sample or figure out a piece of the puzzle, we're participating in something larger. We're continuing a project that started when the first human looked up at the moon and wondered what it was, a project that spans cultures, centuries, continents, a project that connects us to the past and to the future. The Apollo astronauts who walked on the moon in the 1960s and 70s are old now, or gone, but the rocks they brought back are still here, still being studied, still revealing secrets, and the astronauts who will walk on the moon in the coming years haven't been born yet, or they're children now, looking up at the night sky and dreaming. The project continues, the questions continue, and the moon, patient and silent, waits for us to figure it out. We'll return to this shortly, but first, let's think about what it would mean, not just scientifically, but philosophically, emotionally, if we really did once have two moons. What does it change about how we see ourselves, our planet, our place in the cosmos? There's a kind of loneliness in the idea of two moons. Not the loneliness of being alone in the universe, but the loneliness of loss, of something that was once there and then wasn't. A companion in the sky, not just for Earth, but for the moon itself. And then one day a slow collision, a merging, and suddenly the moon was alone. Of course, the moon doesn't feel loneliness. It's not conscious. It's a ball of rock, following the laws of physics, orbiting Earth because gravity says it must, but we project onto it. We always have. The moon is a mirror for human emotions, human stories. We see faces in its craters, we tell myths about its phases, we use it to mark time and navigate and dream. And if there really were two moons, then those myths would have been different. The stories would have been different. Maybe one moon would have been male and the other female. Maybe they would have been siblings or lovers or rivals. Maybe one would have been the bringer of light and the other the guardian of darkness. We'll never know because those stories were never told. There was no one to tell them. But the idea lingers, the idea that the sky was once different, that the world was once different, and that change, even cosmic change, is part of the natural order. Nothing lasts forever. Not stars, not planets, not moons. Everything is temporary, everything is in motion, everything is becoming something else, and maybe that's the real lesson here. Not whether Earth had two moons, but that even the things we think of as eternal are just moments in a longer story. The moon we see tonight is not the moon that will be there in a billion years. Its orbit will be higher, its face will be more cratered, its influence on Earth will be weaker, and in a few billion years more, when the sun swells into a red giant and engulfs the inner planets, the moon will be gone entirely, vaporized or flung into space or swallowed by the dying star. That's a long time from now. So long that it's almost meaningless to think about. But it's still true. The moon is temporary, Earth is temporary. We are temporary. And that's okay, because temporary doesn't mean meaningless. A moment can still matter, even if it ends. The two-moon hypothesis, if it's true, reminds us of this: two moons, orbiting Earth for a few million years, and then colliding, merging, becoming one. A brief chapter in the history of the solar system, but a chapter nonetheless, and even though there was no one there to see it, even though it left only subtle traces that we're still struggling to read, it happened. It was real. It mattered, in the sense that it shaped the moon we have today, and the moon shaped the Earth, and the Earth shaped us. So maybe this question isn't just whether we had two moons, maybe the question is what we do with that knowledge, assuming we ever get it. How does it change us? How does it change how we think about the cosmos, about time, about change and loss and becoming? I don't have an answer to that. I'm not sure anyone does, but it's worth thinking about, worth sitting with, because the universe is vast and old and strange, and the more we learn about it, the more we realize how much we don't know. And that's humbling. But it's also exhilarating, because it means there's always more to discover, always more to wonder about, always more question waiting in the darkness. Next, we'll bring this to a close, not with a definitive answer, because we don't have one, but with a pause, a moment to look up at the moon, singular as it is, and appreciate the mystery it still holds. So here we are, at the quiet end of the question. After all the orbits and impacts and computer simulations, after all the geological maps and chemical analyses and thought experiments, we're left with something simpler. A question that doesn't have a clean answer yet, and might not for years or decades. Did Earth once have two moons? Maybe. Maybe not. The evidence leans in interesting directions, but it doesn't shout, it whispers, and science, when done carefully, listens to whispers, but doesn't mistake them for certainty. What we know is this: the moon is lopsided. Its far side is different from its near side in ways that are hard to explain if it formed as a single symmetrical object. The two-moon hypothesis offers one explanation, an elegant one, grounded in processes we've seen elsewhere in the solar system. A slow collision, a gentle merging, two worlds becoming one. But there are other explanations: tidal heating, asymmetric cooling, variations in the impact history. The moon is old and it's been through a lot, and disentangling all the different processes that shaped it is difficult. Every new piece of data helps, but it also raises new questions, and maybe that's okay. Maybe the uncertainty is part of the story, because the universe doesn't owe us easy answers. It doesn't package its mysteries in neat boxes with clear labels. It gives us fragments, clues, hints, and we do our best to piece them together, knowing that our picture will always be incomplete. But incomplete doesn't mean worthless. Even if we never know for certain whether Earth had two moons, the question itself has been valuable. It's pushed us to look more carefully at the moon, to think more deeply about how moons form and evolve, to develop new tools and new methods for studying the past. It's connected us to the broader story of the solar system, reminded us that our little corner of space has a history, a long and complex one that stretches back billions of years. And it's given us something else, something harder to quantify. A sense of wonder, a reminder that even the most familiar things, the things we see every night, can still surprise us. The moon, hanging there in the sky, constant and unchanging, as far as our short human lives can tell, is actually a record of violence and change and slow transformation. It's a world with its own story, and we're still learning to read it. So tonight, or whenever you next look up and see the moon, maybe take a moment to imagine what it might have been like if there were two pale disks tracing different paths across the sky, two sets of tides pushing and pulling at the oceans in complex rhythms, two shadows crossing on the ground, and then imagine them drifting together slowly, inexorably, until one day they touched, until their surfaces crumpled and merged, until the sky changed, became simpler, became what we know now. It might have happened, it might not have. But the possibility is there, written into the moon's strange asymmetry, waiting for someone to prove it or disprove it. And until then, the question remains, a quiet mystery hanging in the sky, patient and still. You are part of this now, just by listening, by following these thoughts into the darkness, by wandering along with scientists and dreamers and everyone who's ever looked up and asked, what if? Because that's what we do. We look, we wonder, we ask. And sometimes, if we're patient enough, the universe answers. Sleep well, traveller. The moon, whether it's one or two or something stranger still, will be there tomorrow night, and the night after, and the night after that, watching over us, keeping time, holding secrets in its ancient stone, and maybe, just maybe, remembering a companion it lost long ago.